Hello everyone, very good evening. Kindly confirm if audio video is clear. Very good evening everybody. Please confirm if audio video is clear so that we can proceed. Okay, everything is fine. Thank you very much. So let's begin the session. This is our fourth session on the concept of set theory and linear algebra. So let me first tell you that what did we discuss in the last class. In the last class, we have started with the concept of equivalence relation. What is an equivalence relation? Sir, a relation which satisfies three different properties, that is whether this relation is reflexive, symmetric and transitive. If these three properties are satisfied, then that particular relation is called equivalence relation. Clear, Dinesh? Okay. Now, then we said that's okay, it's fine that equivalence relation is okay, but then we started the discussion of partition of a set. So, what is a partition of a set? If we divide a set into non-empty subsets, what's please mind it? If we divide a set into non-empty subsets such that every element of the original set is present in exactly one subset, then we say that it is a partition. So that's what we discussed in the last class. So anyway, let me explain. You may be thinking that, sir, this particular lecture is for partial order relation. And today we will cover the pendency. So actually the problem is that yesterday we were supposed to complete all these things, but because of the discussion of different types of relation, we could not complete it. So today I'll complete all these three topics along with partial order relation. Don't worry about that, right? So we'll understand what do I mean by equivalence class. We have already seen the partition of a set. So we'll again try to understand that how many partitions will exist for a given set of a particular cardinality. Apart from that, we'll try to see the number of equivalence relations which are possible on a set. We'll try to understand the correspondence between number of partitions and number of equivalence relations on a set. Anyway, let's begin. That this is from the last class. We said equivalence relation is nothing but a relation which is reflexive, symmetric and transitive. I give you certain examples. Apart from that, I defined the concept of partition. So what is a partition? If there is a set A, if we divide this set A into non-empty subsets A1, A2, A3 up to AK, then the set of all the subsets will be called a partition, provided that the intersection of any two distinct subsets of this set must be disjoint. So what does it mean? That none of the element of set A should be present in more than one set, and the union of all these subsets must be equals to A. That is, all the elements of this set A must be present in at least one subset. So not in more than one, but at least one, that is exactly one. Not first definition says that element is not present in more than one subset, and second definition says that element is present in at least one subset. So not more than one and at least one means exactly one. Clear? So this is the partition. So I just told you, give you the example that let's assume 1, 2, 3, 4, 5 is a set. Then I said that empty set cannot be an element of the partition. Empty set cannot be the element of the partition. So this is not allowed. Therefore, it is not a partition. Similarly, an element cannot be present in more than one set. So the element 4 is present in multiple sets. Therefore, not a partition. Similarly, it should not happen that any element of the set is left. That means it is not present in any of these sets. So if you look at this, element 4 is not present in any of the subset, therefore it is also not a partition. But if every element of the set is present in exactly one non-empty subset, then it will be called a partition. So you can see 1, 2 intersection with 3, 4, 5 will be pi, that is no element is present in more than one subset. 1, 2 union with 3, 4, 5 will be 1, 2, 3, 4, 5. That means every element of the set 1, 2, 3, 4, 5 is present in exactly one subset of this particular set. Therefore, it is a partition. So you may have number of partitions. You may have number of partitions for a given set. Now let's start. This is your homework problem that I gave you the last class, that find the number of partitions of a set A when mod A equals to 0. Sir, how many partitions will be there for set A if mod A equals to 0? Many of you will say that number of partitions will be 0. No, there will be exactly one partition. There will be exactly one partition of set A when the cardinality of set A is 0. Please try to understand that. If A is an empty set, if A is an empty set, then what will be the partition of this? Sir, what do we include in the partition? If A is the empty set, then partition of A is the set in which there will be no element. Please, 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 it's very important. In the last class, I told you that phi cannot belong to partition of any set. But I said this is an element belonging to the partition. Here, in this case, the partition itself is an empty set. There is no element which is an empty set. No element of this set is an empty set. Therefore, the empty set cannot belong. The empty set cannot belong to the partition of our set, but the partition itself can be empty. Partition itself can be empty provided the set itself is an empty set. So there is no subset of this set A which is non-empty. Therefore, no element will be present in the partition of set A. No element will be present in partition of set A. So find the number of partitions I was talking about. So if mod A equals to 0, that is the cardinality of set A is 0, then how many partitions will be there? So number of partitions will be only one, and that will be an empty. That will be an empty. So let me write it on the next slide. First, if mod A equals to 0, then number of partitions of A will be equals to 1. There will be only one partition in that particular case. Let's look at the second case. Sir, let's assume that if set A has the cardinality 1, that is, let's assume there is only one element in set A. Now, how many non-empty subsets are possible of set A? How many non-empty subsets are possible of set A? So there will be only one non-empty subset. There will be only one non-empty subset of this set A, and that will be set A itself. Every set is a subset of itself, so set A will also be a subset of set A. In that case, it will be the only subset which is non-empty. Otherwise, one more subset of this set is phi, but that is an empty set. Okay. So what will be the partitions? Then the only partition of A is a set contains non-empty subset set itself of set A. So there is only one partition. Again, if mod A equals to 1, then also number of partitions of A will be 1. Second, mod A equals to 1, then number of partitions of, okay sir. Third, if mod A equals to 2, then number of partitions of A will be how many? Please tell me. Number of partitions of A will be how many? So let's try to understand this. Sir, if I take the set A as a set of cardinality 2, let's assume if A equals to comma B, then what are the non-empty subsets? What are the non-empty subsets of set A? Sir, one subset will be one subset will be AB. So let's look at this very clearly. Please try to understand. Then partitions of A are so there will be two partitions. These one is the set containing the complete set. Yes, sir, it is also a non-empty subset of the given set. So you can include this in the partition. This is one partition, and Another will be one non-empty subset is A, another non-empty subset is B. Now, if you take the intersection of this two, it will be phi. If you take the union of this two, you will get the overall set A. Therefore, again, it is also satisfying the definition of partition that the intersection must be phi and the union must be equals to original set. So, there will be two partitions. There will be two partitions of a set A if the cardinality of set A is 2. Here, so number of partitions of A will be 2. Now it becomes trickier. The moment we go beyond 2, we will have to understand this. So let's assume let A equals to 1, 2, 3. That is mod A equals to 3. Then how many partitions will be there? How many partitions will be there? If mod A equals to, then partitions of A are this. So one partition will be quite easy. That include the complete set itself into the set. It is one set, sir. Only one set is there, so intersection will be phi. There is no one to take intersection. No two distinct sets are there, and the union of 1, 2, 3 will be with nothing. So 1, 2, 3 itself is the original set. So there is one partition. Another will be, so the simplest one is you can take one different. Now please try to understand. You may say that, sir, another partition will be 2, 3, 1. But please tell me, these are two different partitions or the same partition? These are two different partitions or they will be counted as a same partition. Sir, it is the definition of a set. Within the set you write it 1, 2, 3 or you write it 2, 3, 1 or 1, 3, 2. Whatever, the order is not important within the set. The order is not important within the set. So it will be treated as a single partition. These are not two different partitions. There are 3 factorial different combinations which are possible, but all of them will correspond to this partition only. They will not be they will not be counted uh, individually. Okay. Now, sir, another possibility is, sir, this is when the only set is of size 3. Another is when there are 3 subsets of size 1 each. Now, another possibility is that, sir, you can have one set as 1, 2, another as 3, or you can have one as 1, 3, another you can take as 2, and the third one can be now 2, 3, and come on. So obviously this 3 will be treated differently because 1, 2 cannot be same as 3, 1, 3 cannot be same as 2, 2, 3 cannot be same as 1. Do we have any other possibility? No, sir, there is no other possibility. So how many partitions of set A? Sir, if mod A equals to, no, not here. Sir, if mod A equals to 3, then number of partitions of A equals to 5. Okay, so we have understood the concept that what should be done. Now let's try to understand that how many partitions there, how many partitions there if mod A equals to 4. Let mod A equals to 4. That is set A, the set with elements, 4 elements. Now, sir, how are we actually counting the number of partitions? Try to understand. There are different ways of writing this 4. The 4 can be written as 1 plus 1 plus 1 plus 1. That is, if the cardinality of set A is 4, then we can create 4 different subsets, each of size 1. We can create 4 different subsets, each of size 1, or we can create 2 different subsets of size 1 and 1 subset of size 2. 2 different subsets of size 1, 1 subset of size 2, or we can create one subset of size 1 and one subset of size 3, or we can create 2 subsets of size 2, or we can take a single subset of size 4. So these are the partitions, these are the integer partition of 4, that 1 plus 1 plus 1 plus 4 will be 4, 1 plus 1 plus 2 will be 4, 1 plus 3 will be 4, 2 plus 2 will be 4, it will be 4. Sir, this is exactly same as 3 plus 1, because it's only trying to say that one subset will be of size 1, another subset will be of size 3, or you say that one subset of size 3 and another subset of size 1 is actually the same thing. Is actually the same thing. So if somebody asks me that, so how many partitions are there? So basically, please try to understand this type of partition will be that one set contains one element, another set contains another element, another set containing the third element, another set containing the fourth element. So there will be only one partition of set A. There will be only one partition of set A in which all the subsets will be of size 1. All these subsets will be of size 1. Now my question is that, sir, do we need to write this partitions all the time? No, you need to identify a technique using which you can actually calculate this value. So, sir, out of 4 elements, the first element can be chosen in 4C1 ways, and out of remaining 3 elements, the next element can be chosen in 3C1 ways. Out of remaining 2, the third element can be chosen in 1 ways, and from one element, the remaining one can be chosen in 1C1 way. Now, sir, they all are of same size. When we are counting like this, we are giving importance to the order in which the elements are selected. If you select 1, then you will be left with choices 2, 3, 4 for the next set. If the first element is 2, then you will have the choice 1, 3, 4 for the next set. So the idea is, sir, everything you have counted 4 times, so it will eventually become, it will get divided by 4 factorial. It will get divided by 4 factorial. So 4 into 3 into 2 into 1, that is 4 factorial, divided by 4 factorial will be 1 only. 4 factorial divided by 4 factorial will be 1 only. Sir, we can rearrange this 4 sets of size 1 into 4 factorial ways. Yes or no? We can rearrange this 4 sets of size 1 into 4 factorial ways, but they all are representing the same partition. So it will get divided by 4 factorial. Okay, sir. Next one. How many partitions of this particular size can be identified? So please try to understand. Sir, we need one set of size 1. So out of 4 elements, we will choose 1. And from remaining 3 elements, we will choose another one. And from remaining 2, we need to create a partition of size 2. So it will be 2C2. Now, is it sufficient? No, sir. If you are taking it 1 here and 2 here, or if you are taking 2 here and 1 here, and the third partition is of size 2, that is 3, 4 or 3, 4. So please try to understand, these two are not different, because two sets of size 1 are same. Two sets of size 1 can be interchanged. Therefore, you have counted every combination twice. Therefore, it will get divided by 2 factorial. So what will be the value? Sir, 4C1 is 4 into 3C1 is 3 into 2C2 is 1 divided by 2 factorial will be 2. So it will be 6. There will be 6 such partitions in which there will be 2 subset of size 1 and 1 subset of size 2. Okay, sir. Now let's count the third one. For this third combination, please, sir, we need one subset of size 1. So out of 4 elements, you can choose one element in 4C1 ways, and you can create a subset of size 1. From remaining 3 elements, you can choose 3 elements in 3 ways. Sir, subset of size 1 can never be equals to subset of size 3. Therefore, you don't need to divide it by anything. You don't need to divide it by anything. It will be simply 4. So for this, sir, out of 4, you can choose 2 elements in 4C2 ways, and you can create one subset of size 2. And out of remaining 2 elements, you can choose another 2 elements in 2C2 ways, and you can again create a subset of size 2. But, sir, if you take 1, 2 here, and 3, 4 here, or if you take 3, 4 here, and 1, 2 here, it will be the same thing. Both of them are same. There is no distinction. That means you have counted every pair twice in this approach. So you need to divide it by 2. You need to divide it by 2. So, sir, what will it be? Sir, 4C2 will be 6 into 2 divided by 2 will be 3. Okay, sir. Out of 4 elements, you can choose 4 elements in 4C4 ways, and you will create one subset. So there is only one subset of size 4. 4C4 will be 1. So how many total number of partitions? Sir, 1 plus 6, 7 plus 4, 11 plus 3, 13 plus 1, 15. So if somebody asks me that if mod A equals to 4, then number of partitions I don't know of A will be equals to 15. Next one, I'm giving it to you that what if mod A is equals to 5? I'm giving the solution so that you can actually try by yourself. If mod A is equals to 5, then number of partitions, similar way you need to solve that particular number of partitions of A will be equals to, you guys can try, and there are, you can keep increasing the number of elements, and by performing this or by using the similar concept, you can eventually identify that how many partitions will be there for a given set of a given cardinality. And so, sir, we have understood the partition, but why this concept of partition is so important? That's what we need. Sir, we have discussed the concept of equivalence. We have discussed the concept of equivalence. What is an equivalence? The relation which is reflexive, symmetric, and transitive. So, that's something that we need to identify. Okay. Let's move to the next concept after that, that is equivalence class, and you will realize that why this concept of partition. So, what is an equivalence class? Just note down. Let capital R be an equivalence relation. So, for equivalence class, you need an equivalence relation. Let capital R be an equivalence relation on set A. So, we define the equivalence class for the elements of set A with respect to relation R. For any element X belonging to set A, the equivalence class of X with respect to equivalence relation R is denoted by any notation, but generally the same symbol as greatest integer. So will be denoted by this symbol, and it is defined as equivalence class of X, nothing but set of all elements Y. Equivalence class of X will be nothing but set of all elements Y such that element X relates with Y. So what do you mean X relates with Y? Sir, X relates with Y means equivalence class Y such that X comma Y belongs to R. And you know that it's an order pair. So X must relate with Y. Y relates to X will not be of any importance. Yeah. Anyway, so let's try to understand to detail with the help of an example. So let A equals to 1, 5. Okay. And R is an equivalence relation on set A. R on the, what is R? You can take any equivalence relation on set A. So I am assuming that this one is the equivalence relation. 1, 1, 2, 4, 4, 5, 5. So all order pair must be present because it should be reflexive. The next thing is it should be symmetric. So if you have taken 1, 2, then you must take 2, 1. Taken 1, 2, must take 1. Then take 3, 4, 4, 3. That's it. Let's assume this is your equivalence. Now, how do we define the equivalence class for the element of set A? So, how do we define equivalence class of 1? Equivalence class of 1 is the set of all elements which relate with 1. So, look at this relation. Sir, 1 relates with 1. Therefore, 1 will be number of equivalence class of 1. Apart from that, 2 relates with 1. Therefore, 2 will also be an element, the equivalence class of 1. Is there any other element in this relation which relates with 1? No, sir. Only 1 relates to 1 and 2 relates to 1. No other element relates with 1. Next, so what will be equivalence class of 2? So equivalence class of 2 will be the set of elements which relates with 2. So, sir, here 2 relates with 2, 2 relates with, and here 2 relates with, so 1 will also be part. Now, do you understand that this is a set? Therefore, 2 comma 1 is exactly same as 1 comma 2. Difference. Okay, sir. Sir, how do we define the equivalence class of 3? Equivalence class of 3 will be set of all elements which, or will be set of all elements which relates with 3 in relation R. So 3 relates with 3, yes. And apart from that, 3 relates with 4, comma 4. So what will be equivalence class of 4? So equivalence class of 4 will be set of all elements which relates with 4. So 4 relates with 4 and 4 relates with, so 2 elements will be there in the equivalence class of 4, that is 4 and 3. This is same as 3 and 4, right? Now what will be equivalence class of 5? Sir, equivalence class of 5. Sir, the only order pair with respect to element 5 is 5. That is 5 relates with 5. Therefore, the only element in the equivalence class of 5 will be 5. Okay, now there are some important things to understand, that 1, 2 and 1, 2 are same. So these two are same. Okay. 3, 4 and 3, 4 are same. Also. Now, if somebody asks me that how many distinct equivalence classes are there? How many distinct equivalence classes are there for the elements of set A with respect to relation R? So, sir, this is one, this two are same. Another one, this is, so can I say 3 distinct equivalence classes for elements of set A with respect to equivalence relation R? Okay, in a while you will understand an important thing. Sir, let me first write down those notes so that you will understand. Note. First, equivalence class of element X or equivalence class of element A may be same as equivalence class of element B. So, if equivalence class of element A may be same as equivalence class of element B, even if A is not equals to B. That is, for two distinct element also the equivalence, their equivalence class may be same. And we have an example. One is not equals to 2, but still their equivalence class is same. One is not equals to 2, but still the equivalence classes may be same. So equivalence class of element A may be same as equivalence class of element B, even if A is not equals to B. Second, sir, if you have the equivalence classes for all the elements of set A, then if you create a set of distinct equivalence classes, there are 3 distinct equivalence classes. If you create a set of distinct equivalence classes for the elements of set A, then it will create a partition of set A. This the set of all distinct equivalence classes of elements of set A creates and creates a partition of set A with respect to equivalence relation R. Respect to equivalence relation R. In a while, I'll give you here. Okay, sir. Set of all distinct equivalence class is, sir, one distinct equivalence class is 1 comma 2. Another distinct equivalence class is a set containing element 3 and 4. Another distinct equivalence class is 5. Yeah. Now, please check, is it a partition of this set A? Yes, sir, it is a partition of this set A. Makes sense? It is partition of set. So if you have a set and equivalence relation on that set, then by determining the distinct equivalence classes of the elements of set A, you can create a partition of that set A with respect to given equivalence relation. Please, if you have the equivalence relation on a set A, then of that particular set, you will have, so you will have a unique partition of that set corresponding to the given equivalence relation. Now, that means if you know the equivalence relation, you can obtain the partition of the set corresponding to that equivalence relation. But what if partition is given? If partition is given, can you identify? If partition is given, then can you identify the equivalence relation with respect to which that partition is created? Yes, sir, that is also possible. That is also possible. Write down the no. So if we know the equivalence relation, we can create the partition. But what if equivalence, what if partition is, if partition of a set is given, then if partition of a set is given, then we can obtain the equivalence relation. We can obtain the equivalence relation on that set, or we can obtain the equivalence relation with respect to which that partition is created. Partition created by taking partition is created by performing the self cross product, by performing the self cross product of the subsets the partition and then taking the union of all those cross products. Don't know whether you have understood it or not, but I'll explain that with the help of example. What did I say? Sir, if you know the equivalence relation, you will be able to obtain the partition. But what if we know the partition? Can we obtain the equivalence relation? Take an example. Let A 1, 2, 5 and partition of A 1, 2. This I'm taking the same partition which we have just created with respect to above equivalence relation so that you will be able to cross check. So 1, 2, 4, 5. Let this obtain the equivalence relation. The equivalence relation. So what's the process? What did I say? Step 1. Take self cross products. Should be perform cross product of 1, 2, 1, 2. Then perform cross product of 3. Partition product or cross product is the same thing. Perform cross product of 5. So what will be the result? So if I take the cross product of 1, 2 with 1, 2, I'll get 1 will relate with 1, 1 will relate with 2 will relate with 1, will relate. This is the self cross product of 1 cross 2 cross 1 with 1 cross 2. So what will be the self product cross product of 3 cross 4 cross 4? So it will be finally take the self cross product of 5 with 5, that will be 5. Now step 2, take the union. What if you perform the union of this? If you perform the union, you will eventually see that 1, 1, 2, 2, 3, 3, 4, 4 and 5, 5 are present. Ordering is not important, please. Apart from that, 1, 2, 2, 1 is present. Apart from that, 3, 4, 4, 3 is present. Now, please go back and check. Is it not the same relation? Is it not the same relation as the relation with respect to which we created this partition? Yes, sir. So if you know the equivalence relation, you will be able to create the partition. If you know the partition of the set, then you will be able to create the equivalence relation with respect to which that partition is created. Clear? So next thing is number of equivalence relation. Please try to understand. What do we need to understand? Sir, we need to understand there is a one-to-one correspondence. There is one-to-one correspondence between partitions of set A and equivalence relations on set A. So exactly as many partitions are there, exactly same number of equivalence relation will be there on that set A. That is number of equivalence relation on set A will be equal to the number of partitions of, as equivalence relation changes, corresponding partition will change. As partition change, associated equivalence relation will change. That means for every partition of set A, there will be a unique equivalence relation. Similarly, for every equivalence relation on set A, there will be a unique partition created by that equivalence relation. Therefore, the number of equivalence relation on set A will be exactly same as the number of partitions of set A. So, if we talk about number of equivalence relations, so we already know about the number of partitions. So case 1, if mod A equals to 1, first of all, let's say if mod A equals to 0, then how many partitions of set A? So number of partitions of set A will be 1. So if mod A equals to 0, then number of equivalence relation on A number of equivalence relation on set A will be equals to 1, and that will be the empty relation, Yeah, sir, is it possible for an empty relation to be reflexive? Yes, it is possible for an empty relation to be reflexive if and only if the set itself on which the equivalence relation we are trying to find out is an empty set. So, second, if mod A equals to 1, then number of equivalence on set A will also be. Sir, if you need example, then I can give the example. So A equals to set A. Relation on A order pair consisting of, obviously there is only one order pair with this, that is A. Now please check, is it reflexive on set A? Yes sir. Is it symmetric on set A? Yes sir. Is it transitive on set A? Yes sir. So this is the only equivalence relation on set A. So there is only one equivalence relation on set A if the cardinality of set A. Similarly, if mod A equals to 2, then number of equivalence relation on set A. So we know how many partitions of set A if the cardinality of set A is 2. So number of partitions will be. Let's take an example. Sir, if A equals to AB, what will be the equivalence relations? Sir, equivalence relations on set A are, what are they? So first one will be only take order pair AA, order pair BB, and another will be take all the order pairs, that is take AA, AB. Now please try to understand. Sir, if you ask me that, sir, this particular equivalence relation is with respect to which partition of this set? So with respect to partition, this one partition. If you take A cross A, you will get AA. If you take B cross B, you will get BB. And this one is with respect to partition. Sir, if I take a single subset as AB, then AB cross AB will be AA, AB, BA, BB. So all order pairs. So similarly, you can define that number of equivalence relation mod A equals to 3. We are done? Yes, we are done. 4. Mod A equals to 3. Then number of equivalence relation on set A equals to 5. Already calculated the number of partitions. if mod A equals to 4, then number of equivalence on set A also 15 and so on. There's a concept of bell triangle, but I'm not going to deal it in particular class because anyway, any question that can be solved using bell triangle can be solved if you remember the concept up to this point of time. Or extra, if you need two more things, then 6 and 7 will be. So if you remember this much, if mod A equals to 5, then number of equivalence relation will be 52. And the last one, mod A equals to 6, then number of equivalence relation. So either you can go and study an extra concept of bell diagram, or you can remember these four numbers, that number of equivalence relation on a set A with 3 element will be 5, 4 element will be 15, 5 element will be 52, and 6 element will be 203. Nothing else can be solved using the bell triangle apart from this 6. So it may be used to provide the number of equivalence relation on a set A of any cardinality, but GATE is not going to ask that because they don't want you to mark something. If conceptually they want you to solve the question that how many equivalence relations there on a set A, then they will not go beyond mod A equals to 4. Otherwise, the question itself will take more than 50. And they don't want you to remember anything. So that's the only logic, that you don't need to go with the L number. Okay, so we are done with all those things which we were supposed to discuss last class. That try to understand. Now, I hope you understand equivalence class. We defined for an element of set A with respect to an equivalence. Partition of a set we have discussed the last class, as well as we have understood about the number of partitions on a set A in today's session. And we know that there will be a one-to-one correspondence partition of a set and equivalence relation on set. Therefore, number of partitions on a set A will be exactly same as number of equivalence relation. So we are done with the pending task. Now we'll start with the partial order relation. So what is our partial order relation? Sir, equivalence relation is a relation which is reflexive, symmetric, and transitive. Then what is a partial order relation? What is a partial order relation? Just note down. A relation R on set A is called a partial order relation only if R is first reflexive, the relation must be reflexive. Second, the relation must be anti-symmetric, not asymmetric or symmetric, it will be anti-symmetric. So what's there in these anti-symmetric? Sir, in anti-symmetric relation, diagonal order pairs are allowed, because if you make the relation asymmetric, it can never be reflexive, because diagonal order pair itself are not allowed. So relation will be reflexive, that is all the diagonal order pairs will be present. Anti-symmetric, so anti-symmetric will have no problem because of those diagonal order pairs. But anti-symmetric means if x comma y is present in the relation R, then y comma x cannot be present in the relation R if x is not equals to y. Apart from that, transitive. So your given relation must be reflexive, anti-symmetric, and transitive for that to be called a partial order relation. So first of all, if I define the delta A, my question is it reflexive? Yes, sir. All diagonal order pairs are present. Is it anti-symmetric? Yes, sir. Diagonal order pairs are present. Otherwise, if condition is false, therefore we don't need to worry about then condition. Is it transitive? Yes, sir. There is no problem because of presence of diagonal order pair in the transitive relation. So this is okay. So this is the smallest partial order relation on set A. Diagonal relation delta A is the smallest partial order relation please remember, so this is also an equivalence relation. This is also an equivalence relation. So please remember the diagonal relation on set A is the only relation on set A which is equivalence relation as well as partial order relation. Diagonal relation on set A diagonal relation on set is the only relation on set A is equivalence relation as well as partial order relation. Okay, so sir, can you give us some more example of partial order relation which are not diagonal relation? That equals to 3. First of all, it's flexible. All diagonal order pairs must be present. Then let's say that if I add 1, 2 and 2, 3. So because 1, 2 and 2, 3 are present, so 1, 2 and 2, 3 will force you to add 1, 3 because of transitivity. Now, is it reflexive? Yes, sir, it is reflexive. Is it anti-symmetric? Sir, up to this, it is fine. But for 1, 2, 2, 1 should not be present. So it is not present. For 2, 3, 3, 2 should not be present, which is for 1, 3, 3, 1 should not be present. Okay, let's look for transitivity. They will not create any problem. 1, 2, 2, 2 will be 1, 2. 1, 2, 2, 3 will be 1, 3. Already there. Nothing else starts with 2. So 2, 3, 3, 3 will be 2, 3. Nothing else starts with 3. 1, 3, 3, 3 will be 1, 3. Nothing else starts with 3. So this is just note down. R1 was reflexive. So how did I answer that? Is it reflexive? Yes, sir. Is it anti-symmetric? Yes, sir. Transitive. So look for this three property to check whether the relation is a partial order relation or not. Let's move to the anyway. So I'll discuss them. So next one is partially ordered set. Next one is a partially ordered set. What does it say? A set A set A along with partial order relation R set A along with partial order relation R defined on set A is called partially ordered set. So if you have a set and an equivalence relation, sorry, a partial order relation. So generally, denoted by set name and the partial order are or set. So symbol less than equals to used present partial order. Come on. They may say that this is a partial order, and then they can define that what actually is being represented by less than equals to. I'll give you an example in a while. Okay, come on, let's try to understand. Note, if A is any set of real numbers, if A is any set of real numbers, then A with respect to relation less than equals to a partially ordered set. Sir, how do we denote partially ordered set? So rather than writing partially ordered set, I'll write it as poset. I'll write it as, yeah. So, or generally, it's a very well separate term in the gate questions also. So, if A is any set of real numbers, then A semicolon, sorry, A comma less than equals to is a poset. Why? Why? Because less than equals to is a partial order relation on any set of real numbers. Still not getting it? So let's look at this. A equals to 1, 2, 3. So what will be the order pairs with respect to relation less than equals to? So, sir, an order pair will be present in the relation only if A is less than equals to B. So, sir, 1 is less than equals to 1. Yes, sir, 1 is less than equals to 1. So, it will be present. So, 1 is less than equals to 2. Yes, sir. 1 is less than equals to 3. Yes, sir. 1 is less than equals to 4. Yes, sir. So, 2 is less than equals to 1. No, sir. 2 is not less than equals to 1. Therefore, it will not be present. 2 is less than equals to 2. Yes, sir. 2 is less than equals to 3. Yes, sir. 2 is less than equals to 4. Yes. Sir, 3 is less than equals to 1. No, sir. 3 is not less than equals to 3 is less than equals to 2. No, sir. 3 is less than equals to 3. Yes, sir. 3 is less than equals to 4. Yes. Now, 4 is less than equals to 1. No, sir. 4 is not less than equals to 1. 4 is less than equals to 2. Sir. 4 is less than equals to 3. No, sir. 4 is less than equals to 4. Yes. So, is it a partial order relation? Yes, sir. It is reflexive. It is reflexive. Is it antisymmetric? Only the order pair from one side are available. No order pair from the another side is available. So it will be antisymmetric as well. Is it transitive? You can check. So 1, 2 and 2, 3. Therefore, 1, 3 will also be there. So 1 is less than 2 and 2 is less than 3. Therefore, 1 is guaranteed to be less than 3. Therefore, it will always satisfy transitivity property. So you can say it is reflexive. This is antisymmetric, transitive. Here, all three properties are satisfied, therefore it is a partial order relation. Similarly, let A is any set of positive integers then relation, I am defining the relation, divides, denote it using this or some also. Relation divides is a partial order relation the partial order relation on set A. Come on, you can actually check this. So, with respect to divide, what will happen? A comma B belong to, sorry, A comma B will belong to relation divide if and only if A divides B. Not divided by, I'm saying A divides B. If A divides B, then A comma B will be present in the relation. Okay, so if this is the set, A equals to 1, 2, 3. Now my question is, sir, what will be the order pairs in the relation divide? Sir, 1 divides all these elements. So 1 divide 1, 1 divide 2, 1 divide 3, 1 divide 4. Yes, sir. 2 divides 1? No, sir. 2 divides 2? Yes, sir. 2 divides 2. 2 divides 3? No, sir. 2 divides 4. 3 divides 1? No. 3 divides 2? No. 3 divides 3 only. 4 divides 1? No. 4 divides 2? No. 4 divides 3? 4 divides 4 only. Is it a partial order relation? Sir, first of all, it is reflexive. Is it reflexive? You can check. All order pairs are present. Is it antisymmetric? Yes, sir. Only the order pairs from one side are present. Is it transitive? Sir, if A divides B and B divides C, if A divides B and B divides C, then A will eventually divide C. So, yes, it is transitive also. So, this is a, so you can actually see that divide will satisfy all this three property on any set of positive integers. Therefore, it is actually partially ordered. Next, take one more example. The thing. Let A equals to 1, 2, 4. This is your set. 1, 2, 4, 8. This time, if I take the relation divides, what? If I take the relation divides, then what will be the order pair? Sir, 1 divides 1. Yes, sir. 1 divides 2. Yes, sir. 1 divides 3. Yes, sir. Oh, where 3? 1 divides 2. 1 divides 4. 1 divides 4. Yes, sir. 1 divides 8. Yes, sir. 2 divides 1? No, sir. 2 divides 2. 2 divides 4. Divides 8. Sir, 3 divides 1? No. 3 divides 2. Divides 3. Where is 3? So, 4 divides 1? No. 4 divides 2. No. 4 divides 4. Sir, 4 divides 8. Now, 8 divides 1? No. 8 divides 2? No. 8 divides 4? No. 8 divides 8. Yeah, this is also the same thing. Obviously, it is a set of positive integers. If you would use divide, it will eventually be reflexive, antisymmetric, and transitive. Is it reflexive? Yes. Is it antisymmetric? Yes. Transitive. Yeah. So all three properties are satisfied. Now, the next definition is related to comparability. The next definition is related to comparability. Sir, please, let's look at this. Let R be a partial order relation R be a partial order relation on set A. Elements A comma B belonging to set A. Elements A comma B belonging to set A are said to be comparable. Are said to be comparable with respect to partial order relation R only if A is related to B or B is related to A. So either A is related to B or B is related to A, that is if A comma, that is A comma B belongs to R, or B comma A belongs to R. So you all know that R is a partial order relation. So either A comma B will belong to R, or B comma A will belong to R, because it is antisymmetric. Both can belong to R only if A is equals to B. Both may belong to R only if A is equals to B. So this is the definition of comparability. This is the definition of comparability. That this is how we say the definition that two elements are comparable or not. So please, let's look at this same example. If I copy this and try to explain the concept of comparability, then you'll realize. Come on, let's check. So, in this particular example, if you look at the elements 2 and 3, this example 1, if you look at the elements 2 and 3, what about this? Already know that both of them are partially ordered set. So these are two examples of partial order relation and partial order set. Now, my question is, if we take 2 and 3 are not comparable, 2 and 3 are not comparable because neither 2 divides 3, because neither 2 comma 3 belongs to divide, nor 3 comma 2 belongs to divide. Make sense? So neither 3 divides to 2 nor 2 divides to 3. Therefore 2 and 3 are not comparable. Similarly 3 and 4 are not comparable. Same with 3 and 4. But if you look at 2 and 4, so 2 and 4 are comparable because 2 divides 4. 2 comma 4 belongs to R. 1 is comparable with 1. 1 is comparable with all the elements because 1 divides all the elements. Yeah? So 2 is comparable with 2 and 4. 3 is comparable with 3 only. 4 is comparable with 4 only with respect to this set. Sir, here if you check, 1 is comparable with 1, 1 is comparable with 2, 1 is comparable with 4, 1 is comparable with 8. Now, sir, 2 is comparable with 1. Yes, if 1 is comparable with 2, then 2 is comparable with 1 because either A relates to B or B relates to A. So, in 1 and 2, 2 does not divide 1, but it's fine. 1 divides 2. So, 1 relates to, therefore, 1 and 2 are comparable. So, if you look at this, then in this set, partially ordered, in this set, every pair of element is comparable with respect to relation divide. Every pair of element of set A comparable with respect to relation divide. Hi Aryan. Okay, so that's the idea. So similar way, we can define a new type of relation, total order relation. So we know a partial order relation. We know a partial order relation. So divide on a set of positive integer, the partial order relation. But when exactly it becomes total order relation? When exactly it becomes total order relation? So in a while we will come to that what, sir, a partial order relation is called a partial order relation on set A. A partial order relation on set A is called a total order relation. This year they asked a very good question of total order relation. It's called a total order relation only if every pair of element of set A are comparable with respect to relation R, are comparable with respect to a partial order relation R. A partial order relation R on set A is called a total order relation if every pair of element of set A are comparable with respect to relation R. So look at this. So this is not, so set 1, 2, 3, 4 with respect to device is not a total order relation because there are some pair of elements which are not comparable. But in this example, all the pair of elements of set A are comparable with respect to divide. Therefore, on set A, divide is a total order relation, and on set A, on this set A, divide is not a total order relation. Clear? So basically, total order we define in the terms of total ordered set. So you want divide on A equals to 1, 2, 3, 4 is not a total order relation. Divide on set A equals to 1, 2, 4, 8. You understand every pair of elements are comparable is a total order relation. What is total ordered set? So a total order relation along with set A along with total order relation defined on set A is called a TOE set, totally ordered set. Just like PO set, it's a TOE set. Now please try to understand, before it becomes a TOE set, it will eventually be a PO set. So every TOE set, every totally ordered set is a PO set. So whatever is a TOE set is guaranteed to be a PO set. Whatever is a TOE set is guaranteed to be a PO set because the total order relation will be derived from a partial order relation. So it's actually a PO set. Then we are checking that whether this PO set is a TOE set or not. So it's a partial order relation, but we are checking whether it is a total order relation or not. First of all, it will be a partial order relation. Therefore, every TOE set will be a PO set. But every PO set need not be every PO set need not be a TOE set. Every PO set need not be a TOE set. Clear? So this is related to totally ordered set. So we have seen partial order relation, a relation which is reflexive, antisymmetric, and transitive will be called a partial order relation. Then we have defined a POSET, that is a set along with the partial order relation will be called a partially ordered set. Then we defined the definition of comparability, that two elements of set A will be called comparable with respect to partial order relation R if either A relates to B or B relates to A. So if any one of these two is available, then A and B are comparable, otherwise they are not comparable. Then we said total order relation, that if every pair of element of the set is comparable with respect to your partial order relation, then the relation will be called a total order relation. Similarly, the set along with the total order relation will be called totally ordered set. Whatever is a TOE set is actually a PO set because a PO set will satisfy some more constraint and it will become a TOE set. So every TOE set before it becomes a TOE set is actually a PO set. So every TOE set is a PO set. Every totally ordered set is a partially ordered set. But every partially ordered set need not be a totally ordered set because even if all order pairs are not comparable, then also it is a PO set. If there are some order pairs, so let's look at this, that we are saying that there are some other pairs which are not comparable. It does not mean that it is not a poset. It is actually a poset because it's a partial order relation on set A, so it is a poset. So does not matter whether all pairs of elements are comparable or not. If relation is reflexive, antisymmetric and transitive, then the set along with that relation will be a poset. So poset is a different thing. So every toset will be a poset, but poset need not be. It may or may not be. So this is a poset which is not a toset. It is a poset which is also a toset. So a poset need not be a totally ordered set. So we have discussed some important things. Now these are two definitions for reading purpose. You just read these definitions, try to interpret them. Read these two definitions which are available. So that's one. Just screenshot, or you can pause and you can try. Least upper bound, and this is the definition of greatest lower bound. These two terms, least upper bound and greatest lower bound, are defined with respect to a partially ordered set. So we'll understand these two terms and then we'll try to discuss the concept of Hasse diagram or poset diagram. Hasse diagram is the name, but poset diagram because it is defined for partially ordered set. So that we'll discuss in the tomorrow's class. That will be all for this particular session. So we have understood equivalence relation, partition of a set, equivalence class, the relation between partition of a set and number of equivalence relation on a set. We have also understood the concept of partial order relation. Tomorrow we'll start with the Hasse diagram. Tomorrow start with the Hasse diagram. So that will be very important. We'll again revisit all the concept of partially ordered set when we are trying to construct the Hasse diagram. So we are not done with the concept of poset diagram. For two more sessions, we'll keep discussing the concept of partial order relation and partially ordered set, that is poset. Okay. So don't worry, that will be all for this particular session. Thank you very much for joining. See you tomorrow at 4 p.m. I'm extremely sorry, for some reason I had to reschedule the class from 4 p.m. to 4:30 p.m. but tomorrow there will not be any such issue. So tomorrow's class timing will be 4 p.m. only, in which we will discuss Hasse diagram, how to construct that, what do I mean by minimal element in a poset, maximal element in a poset, minimum, maximum. Then we'll talk about least upper bound and greatest lower bound. How do we check the least upper bound and greatest lower bound for a pair of element by looking at the Hasse diagram. So all those will be discussed in the tomorrow's session. That will be all. Thank you very much. See you tomorrow. Bye bye. Take care. Keep learning.